Hi everyone. Thanks to generative AI, gaming is about to undergo its biggest transformation yet. Beyond just procedural generation, it is now possible to use machine learning to generate fully playable games. From AI-driven storytelling to worlds that adapt in real time, you could say that AI is changing the game. Keep watching to learn more. This video has 3 parts: anatomy of a game, history of content generation, and generating whole games. Part 1. Anatomy of a game. There's a wide variety of different kinds of games out there, of course, and they vary hugely between being very scripted to being more open world style. Some examples of very scripted games are the Never-Ending Story or the original Final Fantasy games. On the other hand, more open world games would include the Mass Effect series and the Elder Scrolls series. An open world game is much more complicated to create because someone had to sit down and manually write out all those different options, all those different quests, all the different world areas that you can go into. Generative AI, of course, promises to change a lot of this. It's possible that every game world you interact with could end up being tailored especially for you. And not just by having some characters there or some characters missing, but by having the entire universe, the structure of it, the actual stories involved completely modified. And if you have an oracle that can essentially generate game content for you, then why not call that oracle at runtime? In other words, the game content could even dynamically change based on your current skill, mood, and desires. I'm not even sure whether you could call that a game anymore. It would basically be more of an interactive virtual environment, almost a dream world. Even small aspects of this have really made some games in the past. For example, I had a friend who just loved playing Left 4 Dead 2 because there was some kind of AI engine that would figure out how well you were doing, how well you were interacting with your teammates, and create just the right zombie horde for you to deal with. And that was the part that made the game so interesting, that it met you where you were and made sure that you were having an interesting and engaging time. Quick word about addiction. Like social media, games are designed to be addicting. All the little numbers flashing and all the little power-ups you can get that make you feel a little bit stronger all the time, all the sound effects and all the loot add up together to be a constant flow of dopamine. Some games are very, very good at this, but nevertheless, there's still a limit to how far they can go in terms of engaging with you, the player, because they have a set universe of different worlds and scenarios that they can present you with. So I think it's quite likely that when you have a system that can generate specific content just for you, that it could be even more addicting. So that's definitely a sober angle to consider before we jump straight into a sci-fi world where everyone is plugged into the computer all the time, because that's the easiest way to feel happy. That aside, games are actually very interesting, not just because they're fun to play, but because they're technically challenging to create. A lot of games will push the boundaries of what the hardware is capable of. In fact, games used to be the primary driver behind new GPU technology. They probably still are, but I imagine AI is catching up there. Additionally, to make a game, you need expertise in a huge range of disciplines. For instance, the actual game engines are highly performant, often written in C++, and extremely complex with physics simulators and dynamically pluggable subsystems and a scripting language like Lua or Python added to it, and different time ticks for graphics, for networking, for player input, for AI. So that's what game programmers take care of. But in addition to programmers, you need level designers, artists, scripters to write the Lua/Python, translators, musicians, voice actors, etc. The list goes on. Unfortunately, however, it's not a very lucrative job to work in the games industry, generally speaking. It's very high stress due to the structure of game projects. They would usually hire on a bunch of people at the beginning of a project, keep them on until the game is released, and then let them all go. So you're constantly on these sort of medium or short-term contracts. The salaries are low, probably because there's lots of people that want to get involved in making a game because it sounds like such an interesting job. And I agree, I think it is an interesting job, but let's talk a little bit more about how AI will affect this job in all of its various facets. Part 2. History of content generation. Content generation is the focus of this video. That means basically creating all the assets like the artwork and the music and the effects that are going to be used in any given game. The storytelling, the voice acting, etc. A game usually consists of the game engine and then the content, to simplify it greatly. The game engine is actually reusable. In fact, a lot of companies will simply rent or purchase a game engine from elsewhere, like for example the Unreal Engine, and then the entire work that they do towards making a game is basically in creating the content. If AI can generate content more cheaply, it will certainly displace a lot of people in the industry. There are, of course, many other ways in which AI is involved in games, including most noticeably in the AI for game characters or NPCs, but we're going to focus on content generation here because it's most related to generative AI, and because, like I said, that basically encompasses a vast majority of the game creation process. The traditional approach is to sit down and draw all the images by hand, construct all the 3D models by hand, create all the scenes by hand with all the lighting and all the effects, along with the story and the actual gameplay. But pretty soon, of course, people started trying to use algorithms to speed up this content creation process. One of the simplest algorithms is just procedural generation. What this means is that you have some code or maybe just a mathematical formula that, when evaluated, can create lots of instances of content for you. Typically, procedural generation will start with one or more random numbers as seeds or random seeds. And starting from those seeds, the algorithm will construct whatever it was designed to construct, like an entire level or an entire texture or an entire 3D model, etc. If you use the same seed and run the same algorithm, you'll get exactly the same output, which is the main reason that procedural generation started to be used in the first place. People realized they could have just a tiny bit of code and then specify a few initial random seeds, and that could generate tons and tons of content. If you've ever installed a game with really wonderful graphics, you'll know that that usually means it's a really large program installation. And this is because the traditional way of creating images and creating assets requires you to then save them onto the computer and ship them with the game. And that adds up really quickly, when basically the only thing the entire team is doing is generating more and more content all day. But if you're using procedural generation, the amount of storage space needed will be tiny. A case in point is the game called kkrieger, which is German for warrior, and I'm probably butchering the pronunciation. But anyway, this was a 3D shooter game with multiple different levels, with all kinds of textures, different weapons, different enemies, and absolutely everything was procedurally generated, even the sounds. And this made the entire executable less than 100 kilobytes. And yes, this game was created as part of a challenge to make the smallest game possible, basically. It's really fascinating to see footage from this game and realize that the whole thing was so small. I'll leave a link to a video in the description below. There are a lot of other famous games that use procedural generation, including the whole Elite series. For instance, Elite Dangerous uses the real locations of all the stars in the galaxy and then uses procedural generation to create all the planets that are orbiting the stars. This way, every player gets something that looks a lot like our Milky Way galaxy, but is going to be randomized and a little different each time they play. The game No Man's Sky takes that a step further and generates the entire universe, including solar systems, planets, weather systems, flora and fauna, creature behavior, artificial structures that you can stumble across, the whole 9 yards. And you can get some pretty beautiful looking images out of that game as well. I'll put one on the screen here so you can check it out. And again, the whole thing is procedurally generated. And perhaps the most famous game of all to use procedural generation is Minecraft. And for Minecraft, a single number, a single seed is used to generate the entire world. And from that you get islands and caves and rock formations and a whole world that actually makes quite a lot of sense as you explore it. Oh, and I should also mention nethack or dungeon crawl. If you've never played those before, definitely check them out. It's probably the most inventive use of procedural generation I've ever seen. And going beyond procedural generation into just using general AI to help with content generation, I think the simplest to describe is using algorithms to generate levels, especially for games where a lot of constraints are needed to make a level playable. If you imagine a puzzle game, for example, all the different elements have to be in very precise locations so that the player can actually traverse from one end to the other. So to generate this type of content, it really helps to have a simulation of the player, an agent, if you will. And you probably combine a lot of randomized feature placement with some, for example, genetic algorithm that combines interesting things with other interesting things to build more and more complex levels. Or you might use other algorithms like OR trees or local search. I think a lot of the time when this is done, you can't really tell by the final game because they spent all the time going through the search space looking for something before including that final result in the end game. A level could be human created, fully AI created, or a bit of a mix. The skeleton created by a human and the details filled out by AI, for example. Another interesting example of this, which I saw at AAAI, is using diffusion networks to do terrain generation. The paper, which I'll include in the description below, basically just incorporates 10,000 different images from NASA to learn different terrain features like rivers and basins and mountain peaks. The system then allows the user to actually interactively sketch different things that they want to have on that terrain. And they use a clever multi-level synthesizer where each level knows how to generate structural, intermediate, and fine-grained terrain features. So again, you could easily envision using this type of tool to generate highly realistic looking terrain and landscapes inside a game, but that would probably not be visible in the final result. The game creators would have been using it as a tool to speed up their process and create something that looked more realistic, and then the end result would probably be baked into the final assets of the game. And of course, you could take it a step further and auto-generate an entire game, but that's the subject of the next section. Part 3. Generating whole games. Generating an entire game is very difficult just because there's so many moving pieces and components. But a paper called Genie recently came out of Google and UBC. I think there were 1 or 2 authors from UBC. And Genie is a model for end-to-end game generation. Actually, the model just generates the content and then it uses the same code to actually play the game. They made a very simple game engine, so to speak. But anyway, this model was basically trained by taking pre-existing videos from the internet, presumably from YouTube, since this is a Google project, and looking for footage of platformer games, 2D side-scroller platformer games. They actually trained a little model by themselves by hand labeling 10,000 examples, and that model would judge whether footage was clean or not. In other words, did it have someone's face in the corner, or was it showing game menus and that sort of thing? And using that classifier, they were able to gather a pretty large data set. It had about 7 million 16-second clips at 10 FPS and 160p resolution. Yeah, you thought your monitor didn't have very many pixels, but try 160 pixels by 90 pixels. That's what happens when you take the 16:9 aspect ratio and multiply it by 10. So this was their primary data set. They also had another data set collected from robotics training data. It looked like a bunch of video that Google probably had internally from RT2. The researchers basically took all of this video data about how the world works and how the worlds of side-scrolling games work, and they trained the model to predict future frames of the video. It's entirely computer vision based. You have a screenshot of some video frame captured from the game, and it tries to predict the next 4 moves that the player will make, along with what that will actually look like, graphically speaking. And yes, it's predicting the actual pixels that will appear in those future states, including whatever actions the player is going to take, and also including the effects of the game engine itself, like simulating gravity. Of course, all side-scroller games have the same basic mechanics. You can kind of move in 4 different directions and jump, and you will have gravity if you're in the air for any length of time. But nevertheless, it's still astonishing to me that this works so well. Games all look very different, and they have different types of enemies, and they have different rules going on. But from a few million short clips, the researchers were able to get that model to understand them all. This was only an 11 billion parameter model as well, which is high, but is pretty small compared to large language models. Anyway, once you have that model that can predict the future frames of the game, then you can effectively use it to do generation and basically end up with a playable game. The paper as a whole uses a lot of different techniques. It's really chock full of ideas and innovations, and yet it's quite good at describing the steps they actually went through in order to try to make it reproducible, which is a bit unusual for a Google paper. And they even define a sort of mini experiment that can be executed on a single GPU or TPU, and they describe how the reader can go about trying that on their own, from step 1, downloading the data from the internet, all the way through to trying to train customized game scenarios. Because at the end of the day, I guess this model was also trained on language, because you can ask it for some particular scenario, just in English text, like bouncing purple balls on an alien planet, or whatever you can think of. Then the model will go out and create a game in the side-scrolling genre that tries to implement exactly what you described. Like I said, it's astonishing that this works as well as it does. The system was even able to predict parallax, which is a Star Trek sounding word that describes a lot of side-scrolling games. Basically, the idea is that you have several layers that are being displayed graphically on the game, and the closest level moves really quickly if the player moves along with it, while the middle layer moves a little bit more slowly, and the far layer moves the slowest of all. This was originally a kind of dumb way to try to emulate distance, to try to make it look a little bit more 3D, PC, back when computers weren't really capable of doing much more. But this model, when asked to predict the visual representation of future frames of that game, will take parallax into account. So it really has a pretty deep understanding of what's going on in a game engine's graphical component. So are our games about to be all completely generated by models? Well, I don't think so, because a lot of work went into this particular model, and it's far more likely that systems like that sketch-based terrain generation one are going to be deployed, because that still allows the humans to be creative and to come up with really engaging content while abstracting away some of the nitty-gritty details and allowing the AI to take care of them. What is fun to think about, though, is what will happen to the game space once the barrier to entry is much lower. When anyone can basically come up with the idea for a game and quickly prototype it or test it out, I think there'll be a lot more inventiveness out there. In fact, in the Genie paper, at the end, they say that the children of one of the authors actually tried out the system, thereby becoming perhaps the youngest game designers ever. It might have a similar effect that YouTube had on videos. You're now able to see videos from smaller content creators, such as myself, when prior to the internet, you'd really only see TV shows and things with large budgets. One final note, sometimes the game itself might just be generative AI. For example, text-based adventure games used to be really popular. You're basically given some text that describes a scenario, and you can write a couple of different words that describe actions that you want to take, and you proceed like that. I haven't checked, but I bet there's a resurgence of those types of games now that we have large language models. And there's a fun little game called Infinite Craft, where you start with 4 basic elements, the 4 fantasy elements of fire, earth, air, water, and you can combine them together. For example, fire and water makes steam. It uses an LLM to figure out what might actually be generated when you combine 2 different notions. So you can try to explore forwards and end up with things that have never been found before, or you can try to work backwards and say, I want to end up with tea, and try to figure out how you can make that from your basic elements. It's a really tiny game, pretty playful, and a really good example of the types of things we can create now that we have more generative AI. I'll leave a link to Infinite Craft in the description below if you would like to check it out. Finally, in conclusion, games were traditionally created one time, statically, by a huge team of human designers, programmers, artists, etc. The advent of generative AI would allow us to take some of that creation process and move it to runtime, so that as you're playing the game, it might change. Or as you're playing the game, you might see something different from your friend who's playing the same game. An early version of this was procedural generation, where you can start with one or more random numbers, random seeds, and then run some algorithm to generate the game content for you. Procedural generation is really powerful, but you have to still write a specific algorithm that will generate useful and playable content. Prime example of this is Minecraft. It's pretty great, right? Every world that you get is playable to one extent or another. But you could also imagine using more sophisticated AI techniques, for example, genetic algorithms, to sort of combine together different versions of a level that you know are playable to try to end up with more complicated and more interesting, but still playable levels. That could happen at runtime while you have the game on your computer, or it could also happen, again, while the game is being created by the human designers. And going even beyond that, we can see that AI can now generate entire games from scratch, just with a single sentence description of what you want the game to look like. And I can't believe I'm saying that, because I did look into some of the research in this area a few years ago, and it was very primitive in comparison. We talked a lot about the Genie paper out of Google, which basically uses computer vision to look at the frame displayed by one game and then predict the future frames, including the player's movement and the effects of gravity and other game rules. Using this model for generation instead of just prediction of future frames is what allows that seemingly magical ability to start with a simple sentence and end up with an actual game. If you keep watching this video to the end, I'll include a clip of that actually happening. Nothing drives home more the fact that we are entering the future than by just writing a little bit of English and then watching a game world pop out of it. It's like a Star Trek computer. You just ask it what you want and you get something pretty cool out of it, as you can see here. And of course, you can do this over and over over again for as many new games as you like, more than enough to keep every person amused within their own little universe. If you liked this video, check out this previous one I made where I talk about why GPUs are used for AI. GPUs, of course, were designed for games, but by a twist of fate, they ended up being really useful for AI training. It's a bit technical, but I think you'll like it. Well, that's all I have for today. Thank you very much for watching. Bye.